Solutions of a system of linear equations. Let us consider a system of simultaneous linear equations in three variables x, y and z as a1x, b1y, c1z equal to e1. Similarly, this equal to d2, c is equal to d3. This is called as the system of linear equations, means or the simultaneous system of simultaneous linear equations. As you know that these are individual or linear equations in x, y, z, and the combined solution of these three equations is called as the simultaneous linear equations, solution of a system of simultaneous linear equations. That is, particularly here we have to find out the solution of a system of simultaneous linear equations involving n equations and n unknowns. That is, number of variables is equal to number of equations. There are two types of system of linear equations, that is homogeneous system and non-homogeneous system of equations. If the constant term in the right side are all 0, then that is if d1 equal to d3 equal to d2 equal to d3 equal to 0, then above system of equation, that is equation 1, is called as homogeneous system of equations. If at least one of the d1, d2, d3 is non-zero, then it is called as non-homogeneous system of equations. So there are two types of system of equation, that is homogeneous and non-homogeneous. If the constant terms in the right side are 0, then it is homogeneous. If at least one of them is non-zero, it is non-homogeneous. For example, this is a non-homogeneous system of equation. It is 2, it is 0, so at least one of them is non-zero. It is homogeneous, it is non-homogeneous. Solve followings. Suppose you have to solve the system of equations x plus y equal to 2, 2x plus 3y equal to 5. Suppose you have to solve these equations by using elimination method. So here the coefficient of x is 1, here the coefficient of x is 2. So now multiplying 2 in equation 1, we get 2x plus 2y equal to 4, 2x plus 3y equal to 5. By subtracting this, we get y equal to 1 and x equal to 1. Suppose you want to solve this, x plus y equal to 1, 2x plus 2y equal to 3. Now solving this, we get 2x plus 2y equal to 2 and 2x plus 2y equal to 3. By elimination method, we get the left side is 0 and the right side is minus 1, which is not possible. So this system of equation has no solution. Suppose consider another system of equation, x minus y equal to 1, 2x minus 2y equal to 2. Now here multiply, if you take common 2 from this equation, we get again the same equation, x minus y equal to 1. So these two equations are same. If you put x equal to y plus 1, that is x equal to y plus 1. So for different values of y, we have different values of x. So this system of equation has infinitely many solutions. For example, if you put x y equal to 0, then x equal to 1. If you put x y equal to 1, then x equal to 2. If you put y equal to 2, x equal to 3. That is, we have infinitely many solutions for this system of equation. So here the important condition is that a system of linear equations may have unique solution, or infinitely many solution, or no solution. For example, here the first one has unique solution, and the second one has no solution, and the third one has infinitely many solutions. So a system of equation may have unique solution, may have infinitely many solution, may have no solution. So first of all, what is the geometrical meaning of it? As you know that x plus y equal to 2 is represent an equation of line. This also represent an equation of line. Now solution of these two equations means we have to find out the common values of x and y which satisfy both equations. That is, here these two equations are two different lines, and these two lines are obviously non-parallel lines because slope of this line is minus 1 and slope of this line is minus 2 by 3. As you know that slope of ax plus by plus c equal to 0 is minus a by b. Here slope of this line is minus 1, here slope of this line is minus 2 by 3. As these two are different, so they are non-parallel, so they must intersect, and the intersection point is the solution of these two equations of line. Here the intersection point is 1 1, so solution of this system of equation is 1 1. Here x plus y equal to 1, 2x plus 2y equal to 3. Here slope of this line is minus 1, slope of this line is minus 1. This means these two lines are parallel. So two parallel lines are intersect at infinity. So there is no intersection between points between these two lines. So there is no solution for this system of equation. If you consider for this case, these two equations of lines are identical, as x minus y equal to 1, 2x minus 2y equal to 2. By taking common 2 from this equation 2 we get x minus y equal to 1. That is, these two lines are identical. So all points on the line are solution of this equation, system of equation. So there are every point on the line represent a solution of this equation, system of equation. So this system of equation has infinitely many solutions. So a system of equation may have unique solution or infinitely many solution or no solution. The most important thing, a system of equation having solution, that is maybe unique, maybe infinitely many, is always said to be consistent. A system of equation having no solution is inconsistent. So a system of equation having solution is consistent, having no solution inconsistent. Now solution of a non-homogeneous equation by determinant method. Suppose you have to find out the solution. Suppose you have to solve the system of equation by using determinant method called as Cramer's rule. If the system of equation is a1x plus b1y equal to c1, a2x plus b2y equal to c2, then x equal to dx by d, y equal to dy by d, where d equal to a1 a2, determinant of a1 a2 b1 b2. That is the determinant of coefficient matrix. Here the coefficient of x are a1 a2. The first column is a1 a2 and the second column is the coefficient of y, that is b1 b2. The d is a1 a2 b1 b2 and dx is, and the dx here, the x is the subscript, it is not the d into x. So here dx is found by eliminating first column in d and replacing the constant in the right side of the system of equation, that is c1 c2. That is, we have to replace the column 1 of d as c1 c2, c1 c2, and it is again b1 b2. Similarly dy, that is, we have to replace the column 2, that is coefficient of y in d, by the constant c1 c2, that is a1 a2 c1 c2, and d not equal to 0. If here d is this, dx is this, and dy is this. So in the system of equation is now proof, given the system of equation is this, we can write this minus this equal to 0. Now by using cross multiplication, we can write x by this, x by minus b1 c2 plus b2 c1. Similarly y by minus c1 a2 plus c2 a1 equal to 1 by a1 b2 minus a2 b1 by using cross multiplication. So we can write x by determinant of this, y by determinant of this, 1 by determinant of this, which we referred as dx, this as dx, and this as dy, and this is d. So x by dx equal to y by dy equal to 1 by d. So x equal to x by d, y equal to dy by d. There is another proof of this theorem which were studied later after completion of some more properties of determinant. Solve the following by Cramer's rule. X plus y equal to 2, 3x minus y equal to 2. Here d equal to the d or del, we represent d or del, the same thing. D or del is the coefficient of the determinant of the coefficient matrix. Here coefficient of x are 1 3, 1 minus 1, y are 1 minus 1, so it is minus 4, minus 1 minus 3 minus 4 not equal to 0. Again dx or del x or d1 or del 1, they are same thing. That is, you have to replace the first column as constant, that is 2 2, in place of first column, that is 2 2 1 minus 1, which is again minus 4. Again dy or del y or d2 or del 2, they are also same. That is, we have to replace the coefficient of y column, that is column 2, as constant terms in d, that is 1 3 2 2, again it is minus 4. So x equal to x by d 1, y equal to dy by d, that is 1. Here the d is, if a1x plus b1y equal to c1, a2x plus b2y equal to c2. Here the coefficient matrix is a1 a2 b1 b2, and its determinant of this is d. Again dx or d1 is formed by eliminating first column of d by the constants c1 c2. Similarly dy is formed by eliminating column 2 and replacing the constant c1 c2 in d. Suppose take another example. This here d equal to the coefficient determinant of the coefficient matrix 1 1 1, 2 minus 1 1, 1 minus 1 minus 1, that is this. Now you solve it, determinant equal to 4. Again to find dx, we have to eliminate the column 1 and replace the constant, that is We have to eliminate this 1 to 1 as 1 0 1 and remaining as same in D. Similarly dy, as we have to eliminate column 2 and replace the constant, that is 1 to 1 1 0 1, this again dz is same. So again x equal to x by d, y equal to dy by d, z equal to dz by d. Now the number of solutions of a system of linear equations. Suppose the system of linear equations is given, find d or del, the determinant of the coefficient matrix. First of all, we have to find d. D is either non-zero or 0. If d is not equal to 0, there is nothing to prove, that is the system of equation has unique solution. If d equal to 0, then system of equation may have, system of equation may have unique solution, or infinitely many solution, or no solution. For example, here d equal to, in this system of equation, d equal to 1 2 1 3, which is 3 minus 2 1, not equal to 0. In this matrix d 1 2 1 2, which is 0. In this system of equation d is 1 2 minus 1 minus 2, it is again 0. Here d equal to 0, d not equal to 0, unique solution. If d equal to 0, no solution. If d equal to 0, here infinitely many solution. So if d not equal to 0, the system of equation has infinitely many, d not equal to 0, system of equation has unique solution. If d equal to 0, maybe no solution, maybe infinitely many solution. Let us solve the algorithm. System of linear equation is given, find d or del. If d not equal to 0, unique solution. If d equal to 0, we have to find out dx, dy, dz. If all are 0, then it has infinitely many solutions. If at least one of the dx, dy, dz is 0, non-zero, then it has no solution. So no solution means inconsistent, infinitely many solution means consistent, having solution consistent, it is having unique solution consistent. So find the number of solutions of following equations. Suppose x plus y equal to 3. If you put y equal to 3 minus x, for different values of x we have different values of y. Obviously this system of equation has infinitely many solutions. Suppose x plus y equal to 1, 2x minus y equal to 0. First we have to find d. Here d not equal to 0, system of equation has a unique solution. So let's take another example. Here d equal to 0. Now you have to find out dx is 4. If at least one of them is non-zero, system of equation has no solution, no need to find dy. Find d. Here d equal to 0, dx equal to 0, dy equal to 0. So obviously the system of equation has infinitely many solutions. Solve the following system of equation by Cramer's rule. Suppose you have to find out the solution of this system of equation. Here d, the coefficient, that is 2 minus 1 1, 1 3 2, 3 2 3, that is this. Now which is 0. If d equal to 0, then we can't say that this system of equation may not have a solution. May the system of equation have solution, have infinitely many solution, or no solution for d equal to 0. So find dx, dy, dz. For all cases dx equal dy equal dz equal to 0. So the above system of equation has infinitely many solution. By using this algorithm, here d equal to 0 and dx equal dy equal to dz equal to 0. So obviously the system of equation has infinitely many solution. That is, as the system of equation has infinitely many solutions, so solution must exist. So put z equal to k, or x equal to k, or y equal to k in any two of the three equations. Suppose you put z equal to k in equation 1 and 2. If you put z equal to k in equation 1 and 2, we can get 2x minus y equal to 4 minus k, and x plus 3y equal to 12 minus 2k, as z equal to k, that is this. Now again now find del, the coefficient 2 1 minus 1 3 7, del x, del y. Now x equal del x by del, y equal del y by del, that is this. So x equal to this, y equal to this, and z equal to this. You can verify for the equation 3. So for different values of k, as k is a parameter, for different values of k we have different values of x, y, and z. Now solution of a homogeneous system of linear equations. Homogeneous means the obviously right side is 0. Here d equal to this and dx equal to, by you have to eliminate the first column and replace 0 0 0. Now as the first column is 0, obviously determinant this value is 0. As the now if you expand this in first column, it is 0. Again dy, the second column is 0. When we expand in second column, it is again 0. dz equal to 0. So compulsorily in a homogeneous system of equation, dx equal to dy equal to dz equal to 0. So if d not equal to 0, the obviously system of equation has unique solution. As dx equal to dy equal to dz equal to 0, so 0 by non-zero 0, 0 by non-zero 0, z equal to 0 by non-zero. So for any homogeneous system of equation having d not equal to 0, solutions are x equal to y equal to z equal to 0, which is called as trivial solution. So yes, similarly, if d equal to 0, the above system of equation has infinitely many solutions, as you know from the algorithm. Here dx equal to dy equal to dz equal to 0 and d equal to 0, so obviously infinitely many solutions, and which are called as non-trivial or non-zero solution. So a homogeneous system of equation is has trivial solution if d not equal to 0 and non-trivial solution if d equal to 0. So obviously a homogeneous system of linear equation is always consistent. It may be unique, may be infinitely many. The most important thing, homogeneous system of equation is always consistent. So for example, find the value of k for which the system of equations this has non-trivial solution. A system of equation has non-trivial solution when d equal to 0, that is this equal to 0, so obviously k equal to 4.